All right, so let's get started. We are very happy to have with us Professor Zaifu Yang. And Zaifu is staying with us under the sponsorship of ERATO KOJIMA Market Design Project. And Zaifu kindly agreed to deliver 4 lectures on dynamic auction design. So the floor is yours.
Okay, yeah, thank you very much. It's my great honor to have this opportunity given by Professor Kandori and also Professor KOJIMA. So I think there are a number of more qualified people to talk about this subject, like Professor Milgram, Auspeer, Gu Stikati. But in this sense, I'm extremely honored to have this opportunity to talk about actually several of my recent work. And also in the first lecture, I will talk about the very famous auction, dynamic auction designed by Gale Sotomayor. And that will be the first part of the first lecture. And the second part, I will talk about the auction for substitutes and complements. The third lecture, I will talk about the very recent dynamic auction designed by Professor Fujishige and I. That auction applies to all unimodal demand types, which is a necessary and sufficient condition for the exchanging economy with indivisibilities. And the last lecture, I will talk about dynamic auction when bidders are budget constrained. So that will be the rough schedule. If you have any question during the lecture, so I will just stop me. But basically, I will leave 10 minutes for discussion in the last part of each lecture. Okay, so basically, almost no proof will be given, but I will give you at least one formal proof for one theorem, and the rest I will just give some indication how to prove some theorems. Okay. Okay, so first I will just introduce some principles of dynamic mechanism design. So basically, of course, this kind of concept you might already know. So first one, incentive issues, strategic issues. We have to make the mechanism to be incentive compatible. Then the second one is about efficiency and privacy preservation. So it's about first efficiency, about allocative efficiency. Then the second one is about information efficiency. So typically, dynamic mechanism has this strong advantage. Then it's about time efficiency. So we should not have a mechanism which takes years to reach a solution. Then the third one is about the rules should be very simple and should be easily understandable. So we might call this procedural efficiency. Then the fourth one is about detail-free. So we should not impose too many assumptions of common knowledge. So this is called Wilson doctrine. Then it's about robustness and error tolerances. So we should have a mechanism which can tolerate misdemeanors or minor offenses. Otherwise, we should have some punishment. So in our dynamic auction design, we will have almost all these essential features. Okay, so in the first part, I will talk about the most favorite model assignment market is just like a house market. Each family, each household just wants to have one house. So this is called the assignment market or unit demand model. And now everyone has cost linear utility in money, and also everyone is supposed to have a sufficient budget. So, so this means that if you say value this house at say 10 million, then you should be able to pay 10 million. That's the assumption typically in the standard auction series. So this is what we in the literature we call you can pay up to your valuation. So in the first lecture we will relax this assumption. Okay. So this model, as you know, it was first started by Koopmans and Beckman. So basically, they proved the existence of a valuation equation, and then Sharpfish actually proved that this model has the set of valuation equation price vectors forms a non-empty lattice. That's the end result. Okay, so look at a simple example. So actually, I have some slides. You can, yeah, maybe distribute it. Later on, I will use this. So here, so you see here, 8 houses and agents, seller and bidders. Now this is a valuation. All valuations are private information of each bidder or each agent. And when we talk about auction design, typically we assume that the seller is honest and the bidders can be strategic, because we cannot achieve both sides strategic approvals. Okay, so this is the information that every agent knows himself, and no one else knows. Then the question is that how should we allocate the houses in an efficient way, and so that also no agent should not be able to manipulate. Okay, so let's look at the details of the model. So we use capital N to denote the set of atoms, and we use 0 to represent the Fermi atom, which has no value or does no harm to anyone, and can be assigned to many number of bidders. And then we use M, capital M, to denote the set of all potential buyers or bidders. And here, so we use a capital VKL to denote the valuation of buyer K on the atom L. Okay, when it's dummy goods, then the value, of course, is 0. And then we use a CL to represent the reserve price of atom with when the good is dummy, the value, of course, is 0. Then we assume all are integer valued. So here, basically, we think that every agent measures the value in terms of units of currency, like yen or US dollars. Okay, so assignment just allocates every buyer with 1 atom, so that no real atom should be assigned to more than 1 agent. So that's the definition of allocation. So it's possible that some real atom might not be assigned, and so also it's possible some bidders might not get any atom. In that case, such a bidder might just get a dummy atom. So we for an assignment, we use this notation U pi to represent the set of all unassigned real atoms. Okay. Okay, the efficiency. So this is everyone familiar concept. So now you have an assignment, and this assignment pi star is efficient if this achieves the highest market value. So you see, this is the value that every bidder gets, and plus the reserve price of all unsold atoms. Okay, this greater than or equal to, you compare with all other possible assignments. Okay, we also use this notation. So this notation, the value of an efficient assignment. So this value will be the same for any efficient assignment. So we call this the market value, and later on, this we will use this value to define the VCG payment, and also the when you have a VCG option, then we also will consider what is the marginal contribution of the each bidder. Okay, so in this case, so for any bidder, if you delete this bidder from the market, then we use this capital M minus K to mean that now this market, now we delete this bidder K. Okay, then we use this SV to denote the market value of the same market. However, the market does not have a value K anymore. So that's the notation we want to use. So this is SV, the market value with all of bidders, and this SV M minus K, the market value without bidder K. Okay, so look at this this market, the same example. So actually, in this market, there are two efficient assignments. So you see here, actually, bidder one should not get any atom, and here bidder four should get house one, if we know these values. Okay, now here there are two possible assignments. So first, okay, we assign house two to bidder two, and then this house three to bidder three, and then the house four is assigned to bidder five. So we have this efficient assignment. Then it's also possible to do it the other way. So this house three is assigned to bidder two, and the house two is assigned to bidder three. So we have two efficient assignment for this market. Okay, later on we will give an option, a dynamic option, which will find such efficient allocation. Okay, competitive equilibrium. So here, okay, feasible price vector means that all prices should be no less than the reserve price. Then we have a demand set. It means that it's the set of given price vector. It's the set of all optimal bundles that the bidder wants to have. Okay, then you have a competitive equilibrium. So here, so every bidder should get an optimal atom, and every unassorted atom, the price should be equal to the reserve price. So that's the point you should pay attention. So the price of any unsold atom should be equal to its reserve price. Okay. Okay, then we have a welfare theorem. Okay, so if P pi is a variation equilibrium, then pi must be an efficient assignment. Moreover, if pi is efficient, there must be another. There must be a feasible price vector such that this will constitute a variation equilibrium. So that's quite easy. Now we introduce the lattice result. So you have a meet and join. The first one, the meet means you have a component-wise minimum of every component of the two vectors, vectors P and Q, and then you have the join that you take a component-wise maximize. Oh, sorry, this is a mistake. This is max. Okay, so for any a set is a lattice. If this you have a meet and join for any two vectors, both will be contained by the set. Okay, then a lattice is complete if it's closed and bounded. Okay, so we have the first theorem by Sharp and Shubik. So this the set of variation price vector is a non-empty complete lattice.
Just a quick question.
Yeah, sure.
So the definition of complete lattice that I'm familiar with is different from your definition. So namely, lattice complete if for any subset of S, there exists a infinite one prima. And is this definition the same as the definition you are presenting here?
This one, yeah, so in this context should be the same, but in other contexts, maybe we have to be careful.
Okay.
Yeah, so because sometimes the terminologies might have different meaning. Yeah, okay.
Because I was not aware of these definitions, I just want to.
Oh, okay, yeah, thank you. Yeah.
This is because S is a subset of any dimensional Euclidean.
Yeah. So now here I talk about in the Euclidean space. Yeah, if it's more abstract, then we have to be careful. Yeah. Okay. So basically, Crawford law presented the first algorithm to find actually it's an approximate variation equilibrium. Then the argument is in order to get the existence of a variation equilibrium for the approximate procedure, you take a sequences of measure sites converting to zero, then the limit will be a competitive equilibrium. So that's the basic idea of Kelso-Crawford. That Dimond-Gale Sotomayor, they present a precise, actually the first algorithm that found a precise variation equilibrium. So that we will immediately discuss this process. So here we assume that all valuations are integer and the size of price adjustment the increment is equal to 1. So this is crucial. Okay, so I said a non-empty set of real atom is over demand at prices P if the number of bidder who demands only atoms in S is strictly greater than the number of atoms in S. Okay, this one we have to be very careful. Demand only atoms in S. Okay, later on. So you see here, this definition. So mathematically speaking, so you see the demand set should be contained by S. So we should not consider the other case, which okay, partly some part of this set has element in S. That's not allowed. And that's not the precise definition. Okay, that's actually the first definition of demand-scale supermajor, and then this one is very crucial. So our demand set S is minimum if no proper subset of S is an over demand set. This is a very, very crucial and also very elegant idea. So then we have an auction. Yeah,
if this is crucial, could you give us examples?
Yeah, we will immediately.
Okay.
yeah, okay. Okay, so now the auction, the idea of the auction actually is very very simple and very interesting. So initially the auctioneer announces a price which is no greater than its reserve price. Okay, then the auctioneer asks every bidder to report its demand set. Then after the receiving all demand sets, then the auctioneer check whether there's over demand or not. If there's no over demand set, then stop. Otherwise, there must be an over demand set. Then in this case, then the auctioneer will calculate a minimum over demand set from the over demand set. Then increase the price of every atom in the minimum over demand set by 1 unit, and then does not change the price of any other atom. Then just repeat this. And this auction will find the minimum variation price vector in finite number steps.
So,
Yeah.
In principle, the auctioneer has to take many subsets of M, right? So,
Yeah, there's a efficient algorithm to find a minimum over demand set if you have an over demand set. Yeah.
Can I make a clarification?
Yeah, sure.
If are there many kind of minimal over demand set, we can choose arbitrary one.
You can choose, yes. Actually, because there are many variants of this auction, so you can also, if you have found several over demand set, then you can also make the union, then make various operations so that you can speed up the convergence of the auction. But here we just take the original version of demand-scale sotomayor. Okay, so let's look at this example. So maybe we look at this one. So you see here why this set cannot be minimum demand set, because we have to think about any purpose of non-empty purpose set should be over demand, right? So you see here, if I delete 4, then 3 is indeed is minimum. Look, 3 is still over demand, right? So if I delete 4, then 3 is over demand, right?
Good question. So
Yeah,
if you have an over demanded set,
yeah,
and if you add any other item
yeah,
where demand is just equal to supply, so only one buyer is trying to buy this additional good. And if you merge this additional good to the original one,
yeah.
it's
then
still a minimum.
yeah,
So over demanded set, except the minimum over demanded set, items in over demanded set may not be over demanded.
So
Like a three for here.
you see here, so this is over demand, right? But it's not minimum over demand, because we have to think about it. We have to consider any non-empty proper substrate of this one should not be over demand. But this 3 is over demand.
Okay, but suppose one's demand is just 3,
Yeah.
item 3 is over demanded.
Yes.
So supply is 1,
Yeah.
and demand is 3.
Yeah.
So just add item 4,
Yeah.
it's still over demanded, 3.
But you can still have over demand, but it's not a minimum over demand.
I know.
Yeah.
So except it's so over demand. So item in over demanded set may not be over demanded.
Oh, that's true.
Like items.
Yeah.
So-
That's true. But so here we just and the basic idea just want to illustrate the orange auction, but there are a lot of variants of this argument to make this. If you have several minimum of demand or over demand, then you can have a number of operations so that you can increase more prices. Yeah.
Here you have 2 minimum over demand.
Yes, so we can
300.
choose one. Yeah.
Okay.
In principle, you can choose 2.
I see.
Yeah. So here, so this is the orange idea of the. So here, so you see here in the last round, then we stop because there's a no over demand anymore. Then you see here we can assign item 4 to bidder 5, item 1 to bidder 4. Then here item bidder 1 should get no item, and you see here 2, 3 you can assign either way, right? So therefore we have 2 efficient assignments. And actually, this price is the minimum variation price vector. So I think here the key point is that we have to be careful what we mean by a minimum of demand set. Sure. Is this clear? Yeah, then we.
Is it always true that if you reach a valuation equilibrium price, there are several, so if there are multiple efficient allocations, can it always be attained by a single valuation price? Like
yeah, I think this is a good question. I think it's yes, but I'm not quite sure. I think most likely is yes.
Okay.
Yeah. Okay, so the first theorem. So this dynamic auction found the minimum V price vector in finite number of steps. Then actually before this paper, Lillard in JPE 83 he considers the same market. He considers a direction mechanism. So actually, what he found is that for this assignment market, the minimum price vector, minimum variation price actually corresponds to exactly the VCG payment. So this means that actually every buyer can get exactly his marginal contribution to the market, so that every bidder will get the payoff. So this is the market value of the entire economy, the entire market minus the market value without bidder K. So this is exactly the marginal contribution of bidder K to the market, to the ground correlation. And what he pays, so is this just his value on the atom plus this difference that is the actually corresponding to the minimum price of that atom. So you can, for then the other result, Leonard proof is correct. Very elegant result is that this one. So truth revealing of every bidder's valuation is actually a dominant strategy for every player, every player.
Quick question.
Yeah.
So in this model,
Yeah.
core and competitive equilibrium coincide in this particular case. And equilibrium price has a lattice structure, so there is a minimum.
Just the minimum.
So let's just suppose those two conditions of core and competitive equilibrium coincide.
Yeah.
And valuation price has a lattice structure, so
Yeah.
you have minimum, infimum, not minimum.
Minimum, yeah.
So under what additional condition this price coincides VCG price? Or without any additional assumption, is it true?
For this assignment, this is true, but for more general market, then we don't have this. Yeah, that's yeah. We will come to actually.
Oh, okay.
Yeah, to that point. Yeah, you go much faster than.
What's the computation complexity of the Donge scale?
Yeah, this is a very good question. No.
Oh, really?
Yeah, it's a. I think maybe for some particular structure, you could have a polynomial option. So, but in general, even for the assignment, I'm not quite sure. Apparently, there's no such a definite result.
Okay.
Yeah. Okay, so actually, demand gear, Sotomayor, they did not discuss incentive issue in the paper, but of course, when you use this two result of Naylor, you can still prove that sensory bidding will be exposed Nash equilibrium for the option. That's not the subject we discussed it. Okay, so this is the first part about the assignment market and the demand scale sort of major market. So in the second part, I will move to the market where every buyer might demand several items. So first case, I will consider the general market with 4 substitutes. Then I will talk about you have substitutes and the complements. So the actually the major. So here, let me briefly discuss one advantage of DJ as auction. So one of the major advantages of this DGS auction over say the Maynard direct mechanism is that here at least every winning bidder do not need to expose all of the valuations. So that's the good, very good advantage of the dynamic auction, because in practice, no businessman want to reveal his valuation or his cost. This is actually extremely important in practice. So, but this auction cannot guarantee to convert to competitive the minimum valuation equivalent price vector if the bidder makes some mistake. So basically, they cannot adjust. You have to modify this algorithm so that when some bidders makes a mistake, then you can still guarantee the process goes to minimum valuation equivalent price vector. You have to modify this one. Okay, so that's okay. So the one of the
About the informational efficiency.
yeah.
So BCZ requires lots of information. You
Yes.
know, huge variation should be transmitted to the auctioneer.
Yeah.
And this Demont-Gale-Shepler auction, exchange of information is very, small.
Yes, very sure.
Prices and demand.
Yeah.
Is it in some sense minimum information exchange?
Mm,
I think I vaguely remember that Ilya Segal has a paper characterizing minimum amount of information needed for resource allocation. So by invoking Segal's theorem, is it possible to show that this is more informationally efficient, right?
yeah, I think he considers a kind of a different model. So I'm not quite sure we can use his idea here, but that definitely that is a very important subject. That how can we measure how much information? How actually what should be the minimum information in dynamic auction design, so that we can still have efficiency. Yeah, that's actually extremely important issue. Okay, so why we want to have auctions or more general markets? So I think the key driving force for this is the sale of radio spectrum license from early 1990s. So there's a huge success of these auctions. And now, for instance, I just give two quite famous auction design. So the first one was by McPhee, Milgram Wilson, around 1995. This was hired by the New York Times as the greatest auction ever. Then the second one was the UK 3G, third generation auction in 2000. That was designed by Paul Brumbury and Kim Binmore, which this auction generated about $10 billion US at that time. So of course, now dynamic auctions have been used in many other places. Okay, so in the second part, so basically I will talk about the double track auction, because this auction will automatically work for GS or substitute market. So let's let's first look at the very celebrated job matching model of Kelso-Crawford. So it's interesting to notice that in that issue, Crawford published two famous papers, with the other one with Sober, in the same issue. Oh, actually, same volume. Yeah. So it's quite amazing. Okay. So what they have done in the paper? So basically, they consider, say, like a manufacturing industry. You have many firms, many workers. So this actually, because workers are indivisible, and each worker just work for one firm. And this market is very thin because it involves indivisibilities. So what they prove is that as long as every firm regards all workers as substitutes, then there exist competitive salaries to support efficient allocation of workers to firms. They actually designed a salary adjustment process. But again, it's an approximate procedure. You take the limit of the increments of salaries, then conversion to zero, then in the end, the co-allocation will convert to strict co-allocation. That strict co-allocation coincides with correlation equilibrium. So that's the idea. And then later on, so this condition actually becomes a benchmark condition for auction markets. So like Paul Milgram, Bruce Lachetti, Osbear, and many others, they use this for auction design. Okay, let me show you what is the so-called gross substitute condition. So you see we have n items, indivisible items. Okay, then we have a utility function. We have a demand set. So Kelso-Crawford define gross substitution in such a way. So now you consider two prices P and Q, and you increase the price, some vectors, some items. Now, what this condition means that now at price P, you have an optimal bundle S. Now, you have already increased some price of items, then you will continue to demand those items whose price have not changed. So this is so you see the price now changed to Q, from P to Q, and this, so now you have a new optimal bundle, and this new optimal bundle must contain those items whose price have not yet changed, but previously you demanded those items. So that's the.
So question, so hidden assumption here is each supply of each item is one, and each consumer can consume at most one, or at most one unit of each item, because utility is defined over the subsets.
Oh, yeah. So
Is this a
in equilibrium model, you can say if you have several identical items, you can still treat them, use different labels. That doesn't matter much.
Okay, so that part is fine, but then, so if we have identical three apples,
Yeah,
you can say apple 1, apple 2, and apple 3.
yeah.
But the price of apples can be different, right?
Yeah,
P1, P2, P3.
Yeah,
So
I
that
think
is allowed.
I got your point. In that case, I think here we need to be a little bit careful when you have say vectors.
Yeah, my question is, this formulation is without loss of generality or not?
Without a loss of generality. Yeah. Okay. Yeah. Okay. Okay. So then Gustacchetti have introduced two very elegant properties of GS. So the first one is called single improvement. What they mean by single improvement? So basically, now you at price P, you take a suboptimal bundle S, then you can always improve this bundle by deleting one atom or by adding one atom or doing both. So this one means. So now you have a suboptimal bundle S. What you can do in order to improve this one, right? So then there are three possible ways of improving this one. One is by decrease one atom, or then you add one atom to S, or you add one to S, or then delete one. So this is this is exactly just a single improvement.
So is it the same as U being M natural concave?
We will come to that.
Okay.
Yeah. So yeah.
Probably some typo. You always ask why 18 as
Yeah. Sorry. This should be S. This yeah. Thank you. Yeah. Just some typo. Okay. Then they also have a second. This condition is very useful later on in the design of Ausbill's auction and also in the 2000 auction design. This probably is extremely important. Then the second condition property called non-complementarity. So you see here at price P, you have two optimal bundles, S and T. Now what you do is that you delete some atoms from S. Then how to make this new bundles to be an optimal bundle again? What you do, you can take some atoms from T. You see, here you have two optimal bundles at the same price as P. Now you take some bundles away from S. Of course, then this will not be optimal anymore. But in order to make this bundle once again to be optimal, then what you can do, you take some atoms from T. Then this will be optimal again. Okay, so basically, it shows that those atoms have no complementarities between them. So, and what Gustacchetti proved is that this.
Sorry,
yeah.
I didn't follow. Or in what sense, intuitively, in what sense, definition 3 shows the non-complementarity?
Okay. You see here. So here, there's you have two optimal bundles. Now you delete some bundle from S, right? So then you just add something from another optimal bundle. But if it's complementary, it means that if you delete something, then the other one you don't want to have anymore, right?
So are you saying that it intuitively shows that there's no complementarity between
atoms in S.
D and items in S
Yeah,
Z minus D.
So basically it means that this atoms in S have no complementarity, because if they are complementary, then if you delete one, then the other one you don't want to have anymore, right? So that's the explanation. Yeah.
So is this equivalent that for all price P, the demand correspondence is a M natural convex set?
Yeah, we will immediately come to that point. So here, Gustachetti, they prove that these three conditions are equivalent. So the order of proving is in this way. It's a little bit complicated, but it's not extremely difficult. Okay. Then Morata showed actually Morata he had developed a theory called, as you know, discrete convex analysis from I think from early 1990s when he was visiting University of Bonn. Okay, so first, Morata introduced what he called M function, that he was in a hyperplane, or that function is not general enough. Then Morata should introduce a much more general class of function, which is called M natural. So for any subsets of N, S and T, and you take A, K from S, but is not in T. So then you construct a function in this way. This is quite ingenious way. So actually, Morata's M function has this part. M function has this part that in order to make that function more general as M natural concave function, then they need to add this part. Of course, this part also is somehow different from the Oringer definition. So basically, the idea is a user projection. So, but this is much more technical. So I will not have time to explain. And Morata probably has talked about this many times. You may have a better understanding than I do. So basically, what Fujishiki Sensei and I we prove that using Gustachetti and other property from discrete mass, there we prove that this M natural concavity is equivalent to GS. So here the difference is that this GS, SA, and NC are defined on the demand set, but the definition form is a precise, also direct definition of utility function. So this, okay, and actually, Oswald Milgram have another also very elegant result about GS. So they define the indirect function with just this indirect function. Then consider the space of prices. You have a submodule function. Then what Oswald Milgram proved that this so the demand corresponds satisfies GS if and only if the indirect function is submodular. So this is also very, very interesting and elegant result. They prove this by using envelope theorem.
This is very easy, right?
In some sense,
Yeah.
yeah, yeah,
But, can you go back to your result?
yeah.
Okay, so it seems that if U is a natural concave, then it should satisfy single improvement.
Yes.
That part may be easy, but the
Yeah.
difficult part is the other.
The other way, yeah, yeah, yeah. Okay, so now just briefly mention what Gosakat in the 2000 paper. So they actually designed a precise algorithm which found a minimum valuation price vector. So it generates the DGS option. So they basically prove the finite convergences by using Matrix theory. And they also show that if actually there's low dynamic option can extract enough information to implement the VCG mechanism for the GS market. So as a matter of fact, this is not surprising because here the minimum valuation prices actually do not correspond to the VCG payment in the general GS market. So you can easily construct an example for slightly general GS market than this the minimum price vectors do not correspond to the.
Okay, so what's the relationship between the set of core and Wallacean equilibrium?
Yeah.
Wallacean equilibrium is always belongs to core.
Yes.
But core is strictly larger than competitive equilibrium.
Yeah, but here I think here they talk about the strategy to prove this. So basically, they show that for this general GS market, there's no way. Yeah,
I have no objection.
yeah. Okay.
A simple question.
Yeah.
Is the core equal to Wallacean equilibrium in GS?
This in principle still this is still true.
Okay.
If you have to restrict it in some way. Because here we have just one seller, right? So here we have to be careful.
Okay.
Okay, so then Osbear actually.
Sorry, I missed your statement. So, what is that? What do you mean when you say no dynamic auction reveals sufficient information to implement the VCG mechanism?
So basically, I think they have something in mind that they try to design a dynamic auction which should extract enough information so that to achieve the VCG outcome. But
So it seems that you need some definition of the dynamic auction to make that statement. So I didn't understand what.
yeah, they made quite a lot of arguments in the paper. So as Hein said, actually, it's quite easy to understand why this cannot be achieved, because in this GS market, the minimum price vector, here we still have a lattice structure of competitive price vectors. However, this minimum price vector does not correspond to the VCG payment. So that's for the assignment.
When it's a dynamic auction, so are you restricting attention to what class of mechanism? Because like
It's basically ascending. I think
so you call the That's what you mean.
Yeah. But now it's quite in some sense now it's quite easy to understand why this is not true. First fact is that this one is not true anymore. For the assignment, it's true, but for more general market, it's not true. So then Osbeer, he proposed a very ingenious dynamic game.
So I remember that statement.
Yeah.
The minimum version price coincides with this VCG
For the assignment.
the assignment option, but not here. So is there any intuition as to why the fact is true for the assignment problem, but not for this case? Is there something?
Yeah.
What's the reason?
So because for any in the environment of post-linear utility, so I think in early years, I think Green or some other number of other people proved that for any mechanism, if you want to achieve strategy provenance, this kind of incentive compatibility, you have to reach the outcome has to be VCG outcome.
Yes.
So that's very crucial.
Yes.
And here, of course, I think they stick to the minimum price vector, but here the minimum price vector does not correspond to the VCG. So how can you achieve that? So then Osbeer, he actually returns to the VCG program, the framework. So what VCG direction mechanism says that you have to consider the margin contribution of every buyer, right? So what is the marginal contribution of every buyer? Is that you consider the original economy with everyone, and then the economy without you. So how many markets you have to consider? In the sense, if you have M agents, M buyers, you have to consider M+1 markets, right? And this is precisely what Osbeer has very, very cleverly used this idea. But this law is this idea, of course, is a VCG, but his idea is that, okay, you use a dynamic auction for all N+1 markets. So the original market, and then every market, you delete one agent, one buyer, sorry. Yeah.
Let me follow up with Peter's question.
Yeah.
So you have a precise definition of VCG payment over there, and you have the evaluation payment.
Yeah.
And those two things coincide if you have assignment in
That's true.
assignment.
Yeah.
Okay. And they are not equal. So our question is why?
Why?
So easier one may be assignment case. So why in the assignment case is VCG payment is
Okay.
based?
Yeah, I think this is basically because you demand more items, more than one items. That I think that's the issue. It's not actually it has nothing to do with GS. So for any markets, if you allow people, each individual to demand more than one item, you can easily have this kind of things. Because normally you would think that it's because of assignment market, you have the impression that, okay, as long as you can find the minimum price vectors, then strategy proof is in some sense it's done, right? But then also, because Goose Katie, they prove that actually for G's GS market, you still have the same lattice result, then it would be very natural to think about if I can find the minimum price vector in the GS market, then it would be very likely to be true that you also have another so-called incentive compatible auction. However, why this is basically, I think it's just because people demand more than one item. That's you cannot construct this
If
thing.
time allows,
Yeah.
let's just check. So K is consuming H.
Yeah,
So P star H is what he pays in Malaysian equivalent.
yeah,
And that should be equal to this Q thing, right?
yeah,
So let's look at the second and the third term. So you exclude me, I am Mr. K.
yeah,
And you look at the total surplus. So originally I was consuming K in
Yeah.
Malaysian market, but I'm gone in M minus K market.
yeah.
So item H can be assigned to some other guy.
Mhm.
And somehow this Q expression boils down to P star. That's our question.
So you see
So I
here,
am K. I'm consuming
yeah.
H.
here you have could you have a number of
No, I'm talking about assignment.
yeah. Oh yeah, assignment market.
So I'm just consuming H in Malaysian equilibrium. I'm Mr. K.
Yeah,
And Q for me has this complicated expression that it boils down to P star H,
yes.
right? And why is that?
Ah.
So that's our question.
Okay. I think that proof it's not
Oh,
it's not so easy.
okay.
It's not so easy.
Okay.
Yeah. So no, it's not so easy.
So I'll think about it.
No. Yeah. No. This
Please go.
yeah. This is not so easy.
Okay.
Sorry.
Okay.
Yeah.
Please go.
Yeah. So sorry for that. Yeah. Okay. So now we will briefly. We still have some time. Let me see. Oh, okay. Should be enough. Okay. So we talk about substitutes. Now we think about complements. So actually, Pomegranate, we first noticed that the exposure problem concerning complements. So later on, we also found that a number of people who are working in auction design, they found that complements pose a challenge for dynamic auction design. So actually, in general, complements have been a difficult issue for economic analysis, not confined to the auction design. So even the older people of Scarf, so he found, before that, Paul Samuelson had a very general statement or result about tautology process as long as goods are perfectly divisible goods. As long as goods are substitutes, then the general tautology process will converge to competitive equilibrium. Then Scarf found a simple example, I think it's 3 goods, they are complements, then the tautology process does not converge to competitive equilibrium anymore. And later on, Paul Samuelson, the great Samuelson, he had a very long paper talk about the issue of complements. So actually, complements or synergies is quite pervasive, also, of course, overwhelming. However, if you just have a casual observation of the reality, this something, of course, you often observe. However, substitutes and complements are often jointly observed. So, for instance, here in the classroom, you see tables and chairs and the computer softwares package and the hardware package. Then if you look at hospitals, so you have doctors and patients. Schools, you have students and teachers, etc. Suppliers and retailers. And then you may wonder whether there's a reason for the existence of such a pattern. And then there's another paper with Gustaketti. They have one little theorem says that GS is almost a necessary condition for the existence of variation equilibrium. And this also has some negative impact on the study of complementarities. So what the previous pattern, so this one, so these patterns, actually we call them cross substitutes and complements in equilibrium model or auction model. Then actually Michael Ostrowski, he found something similar, what he called same size substitutes and cross size complements in a vertical supply chain model. So in AER, I believe that was part of his PhD dissertation. So very remarkable dissertation. Okay, so in the remaining part, I will focus on this market. And so basically, we consider both substitutes and complements. In this special case, then it will be both substitutes, complements. Okay. Okay, so look at this simple example. We have one table, two chairs. Actually, two chairs are identical, and table and chairs are somehow complements. So then you may wonder, so you see here, and who should get what at what prices? So this, so the pattern is similar to everyone, but the values are different. Okay. So now the full model. So we have two groups, two types. So the first group you might think as tables, and the second group you might view them as chairs. Of course, items in the same group could be heterogeneous as well. Okay, then we use N to represent the union of both. And then you have, okay, we still use integer values, and VK is private information. Okay, then efficiently, this kind of things we don't need to repeat, okay? Okay, so here I just very briefly, I use a very simple version, but this definition is the same as the general definition, just to make this definition simpler, easier to understand. So the demand correspondence satisfy the gross substitutes and complement condition. If for any given prices P, now suppose we increase the price of one item, say it could be a table or could be chair. Then the bidder who demands the bundle S at prices will continue to demand items of type J. So we increase whose prices do not change. So like now I increase the price of a chair, then I will continue to demand those chairs I have demanded, but the prices have not changed. And then how about table? Tables, I will continue, I will not demand any items. Previously, I don't demand, I didn't demand. So that's so.
For clarification question.
Yeah.
So in Grant Saketti's definition, sorry, no, the GS definition,
Yeah.
you allowed for any type
Yes,
of change
yes.
from P to Q, where
Yeah.
Q is weekly larger. While here you are talking
Single
about one item, but does it matter at all?
No,
Or does
no,
it-
it doesn't matter.
I
Yeah.
see, thank you.
Yeah.
Another question is, in the GS definition, you had for all S, which is in the demanded at P,
Yeah.
there exists, I think, T,
Yes.
in the demand at
So here,
Same to,
here is the same.
okay, so here you also have this,
Yeah.
they exist, and then, sorry, for all, they exist.
Yeah.
Okay.
So, but then the only difference is the other part here. So those, so you see, and we're not demanding any item of the other type. So there's, if the type is first J is a chair, then the other type means table. If you didn't demand at price P, then you will not demand those tables at prices Q. So that's okay. So so if one of the type is empty, then this definition precisely coincides with the GS condition of chlorophore. Okay, now what is the auction? So the auction is actually quite so the basic idea is that we try to minimize the so-called Lyapunov function. Okay, this idea was first introduced by Osbeer. And so actually he proved that for if the market has a variation equilibrium, then the set of equilibrium price vectors actually coincides this the minimizer of the Lyapunov function. So this Lyapunov function is actually is a convex function bounded from below. So this, and we have a okay. We also define the so-called generalized lattice and also generalized submodularity. And for this market, actually, we can still have kind of a lattice structure. That one I will not spend too much time, but I will just very briefly to look at some statements. So for this GS model, actually, we can prove that the set of variation prices forms a non-empty, integrally convex, and complete generalized lattice. So this integrally convex set has a very nice geometry, and again, so we need to generalize the single improvement to this more general model. Now here, so the basic idea is that we try to minimize the Lyapunov function. However, there's a problem because the every agent is strategic. They don't reveal the private information. So in principle, there's no one knows what is the Lyapunov function at all. So this is the first difficulty. So in principle, we can use the idea of minimizing the Lyapunov function. The problem is that we don't know the seller, the auctioneer does not know the near pole function. Okay, then the second question, even if you know the near pole function, then there's a problem which direction you should search. And here, the search direction also plays an important role. Okay, so we need to solve this two problem. Okay, so now we have a so-called sorry. So the so-called double track auction. So the basic idea is that for one group of goods like chairs, you basic idea you start from very, very low price, say from 0, so that every chair will be over demand. Then for tables, you put the price so high so that no one wants to have any tables. Then you have on the one side, you have an over demand situation. Then on the other side, you have oversupply. So then the law of price adjustment is that, okay, you try to increase the price of over demand item and decrease the price of oversupply. So then you have a so-called double track. So two opposite direction. So one side is like a Dutch auction, the other side like an English auction. So that's the rough idea. And here we have a little bit more precise adjustment. So for one side, you try to either increase by 1 unit or decrease by 1 unit or do not move at all. So you start for one group, very low price, for the other one, a very high price. Then this idea is still very similar to the DGS auction. So here, the auctioneer adjusts his price and then ask every bidder to report his demand set. So you see here the demand set. Then here we have a max min problem. So what does this mean? The minimize, this means that every bidder tries to minimize his payment. This is the idea. And then the seller actually tries to find a price adjustment so that she can maximize her revenue. This is the general interpretation of this process. Later on in my third lecture, actually, this kind of a formula holds for all unimodal demand type. And I will show that actually minimize the appropriate function is actually equivalent to this. So the appropriate function is unobservable information. And we can turn the problem of unobservable information to the observable information. So in my third lecture, I will talk about actually this formula is equivalent to solve the minimization problem of the approach function. This one.
Oh, sorry, actually, my question is simple.
Yeah.
What is capital data here?
Oh, capital data. Oh, sorry, capital data. Here.
So that's behind there.
So the price adjustment.
Okay.
Yeah. Okay. So for this simple example, okay, now let's look at the exposure problem. I have a few minutes. I think I can finish. So you see here we have a so-called exposure problem. So exposure problem means that, okay, you every time if there's over demand, you increase the price. But here at step 3, when you increase the price of every atom, then suddenly you overshoot. So this is a simple example of showing exposure problem. And as a matter of fact, is for this one, the double track auctions can easily overcome because we never allow you to increase or decrease both atoms simultaneously. So that's the simple idea. And here you can easily get that. Okay, for the more general case that we have this process. So here, let me be a little bit more precise. So here, maybe I'll try the sentence. I think I have. So basically, this will be efficient assignment. Suppose we know this information. Of course, we don't know. So what the option does is that for 2 chairs, we start from very low price, and for table, we start from very high price. So that we will have this kind of situation. So that every agent. So basically, after auction year collects this information, so the auction year does is is to solve this simple optimization problem. So every step auctioneer just needs to solve this problem. Of course, this problem, if you have a large number of beagles or large number of atoms, it could be still time consuming. Yeah, so I think I will stop here. Thank you very much. Sure.
I have 2 questions.
Yeah.
In this tables on the chairs economy,
Yeah.
Malaysian price doesn't coincide with the VCC payment.
That's right.
But suppose each bidder is only interested in a combination of 1 chair and 1 table.
Mhm.
In that case, maybe no.
No, I don't know.
Okay.
I don't know. Yeah. So I also relate to your question. So there's another open question in this area. So I mean, as long as we know that if the minimum price vector of some sort coincide with the VCG payment, then you, in principle, as long as you can find the minimum price vector, then you can find you can have an incentive compatible dynamic question. And now we don't know what will be the restriction on, say, first example is about on the restriction of GS. So I believe it is possible you have some general GS. However, if you can impose some proper condition, maybe not necessarily artificial, maybe some practical application might have such structure. And that will be very interesting example, research question actually. Yeah, the second one.
Clarifying question. So you have your price adjustment process.
Yes.
Suppose you have only chairs and people have unique demand.
Yeah.
Is your adjustment process equal to demand?
Yeah.
Oh, okay.
Yeah, could be. Yeah. I think we have to make, maybe we have to, I think, no. Should be the same, should be the same.
Should be
Yeah,
some-
yeah, actually, we never sort out. Sorry.
So, is there any other comments or questions?
So if,
Yeah.
regarding the Mitchell first question, so if I understand the Mitchell question is, what happens if you have a unit demand on chair,
Table.
table?
Yeah,
No, we only interested in combination of one chair and one table.
And the answer is that it's still
I don't know.
not the same as this heat, that
I don't know,
you don't know.
yeah, I don't know.
Uh,
So suppose
But
just,
then how about the case in which maybe you always want to get a chair, but let's say your value is for the table is like one,
mm,
and let's say price for the table begins at a very high value,
yeah,
like a high price, then it seems that just reporting my valuation for the table is not the dominant strategy because you could just let's say there's only one one consumer, then I guess he or she can just misreport lower the view.
yeah, so just, this option, if we just take in this way, it's not a strategy proof.
Right.
So we need to actually we have a mechanism which is based on this option, and then we can have an incentive compatible dynamic option. So this is just the basic option. I assume that here every agent bids sincerely. Yeah.
Any other?
Any other questions? Okay, thank you very much for your patience.